Welcome back to the lab. Today we're going to decide whether we should build or buy our hardware for the proof of concept phase of Project Darwin. Remember, we're building a power supply. Even though it's a lot more work, I think we're going to need to custom build our development kit to test out our topology. Stick around to find out why. In a previous video, we decided to move forward with the half H-bridge topology of switch mode power supply for this project. Therefore, the most important requirement for our hardware is the presence of this correct output stage. Another requirement, simply, we need our power electronics to be compatible with many different microcontroller kits. This allows control of the power supply with microcontrollers from different vendors in case one doesn't work out. The third requirement being considered is the power output of this converter. Our target output power is 1 kilowatt for the final design. We need to make sure that this test platform is targeting a reasonable output power that sets us down a path towards that kilowatt. I think 300 watts at a very minimum is a good place to start, but we should set our goal higher than that. With requirements in hand, I set out to find a development kit. The best that I came across in my search was a series of dev kits from Transform. These use GANFETs to demo an inverter stage. This system is designed to allow a microcontroller from TI to slot into the board, which will then take command of the power stage. It includes H-bridge drivers, voltage and current monitoring. They implemented exactly the architecture I had in mind, a half H-bridge with a large power filter consisting of an inductor and capacitor to take out the switching noise. In the reference manuals, they even call out using 100 kHz PWM, exactly the same frequency I had in mind. It even comes with source code. Granted, they do explicitly call out that they didn't finish tuning their control loop, and they only optimized for resistive loads, so there's still some work left to do here. But nearly everything has been done for us. Everything's already finished. What's left to do? Just throw your wallet at the screen and get 4. Be done with this project. Well, there is one glaring issue with the dev kit when compared to our requirements. This would lock us into a specific series of processors from TI, and I really want to give the STM32 series from STMicro a chance to shine. I haven't used any of their processors extensively before, and if I get frustrated with an ecosystem, I want to have my ejector seat back to a microcontroller ecosystem that I know and trust. Not to mention, the dev kit costs $500, and that would be a lot of money to sink into something, considering it'll just become a brick if TI isn't the right choice for our microcontroller. So perhaps my search didn't find every option available on the market. Perhaps I'm being too picky about this whole microcontroller intercompatibility business. Perhaps it's time to design our power supply. Design time then. What are our key specifications? DC bus voltage, which will become our maximum output voltage. DC bus current, which must be able to get the input power up to at least 300 watts with our given DC input voltage. Output voltage and output current, those are also important, but they're derived from our first two parameters, less losses in the system due to inefficiency. Somewhere between 80 and 90% should be where we reside. For this design, I decided on a DC input voltage of 100 volts DC, bus current of 10 amps, and an output current of at least 8.5 amps. Before laying down traces, I put together a quick simulation to verify that the output of this power supply will function as intended. Remember when we made a basic current regulating controller using a few op amps and comparators? It's back in action. Here's what we have. First, the half H-bridge driver, which generates the voltage required to drive the high-side N MOSFET. This requires a charge pump or an additional power supply, since we need to generate a voltage higher than the input voltage for the system. This system requires a PWM input as well, besides just the input voltage. The two MOSFETs in the half-H configuration, featuring a low on-state resistance, create a much more powerful version of that PWM signal through the gate drive ICs. This signal is then capable of supplying hundreds of watts to the load. However, to protect the load from the peak voltages at play and supply a smooth DC, a low-pass filter capable of handling the load current is used. We're using an LC filter in this case because we don't want our filter to dissipate any real power, because that would get burned up as inefficiency. If our inductors aren't rated for enough current, the core will saturate and the design will not function as expected. The regulator monitors the voltage applied to the load with an op-amp configured as a differential amplifier in this case. This will eventually become our microcontroller. The amplifier measures the voltage across the load. The voltage on the load is compared to the reference voltage after being scaled properly. This signal is filtered and scaled again before being finally compared to the 10 kHz ramp signal that's used to generate the PWM. The ramp signal is generated by another voltage source. Since this controller is pretty basic, it can manage to achieve some voltage regulation, but with a ton of overshoot and a lot of ripple. Our controller will need to do better than this, but that won't be hard to do since this one's built out of comparators. Despite its primitive nature, this controller is still capable of achieving voltage regulation. Let me demonstrate by first plotting the reference signal and then dithering that voltage reference a bit, and then we can observe the change on the output. The constant line is the reference voltage multiplied by 20 to show the correlation from reference voltage to output voltage. Then the RMS voltage across the load is darn close to that reference voltage when it's scaled. Let me tweak the voltage reference to change from pure DC to a DC reference with a sine amplitude of 0.2 volts for a moment. This will show the change in input versus change in output. After updating the reference voltage source, we can clearly see the output waveform following this reference voltage. It makes it obvious that we truly have closed loop control in this case of the voltage across the load. I mean, it's not great closed loop control, but it is closed loop control. And this proves that the control algorithm required for this filtered half-H bridge is very, very similar to the control algorithm required for a traditional buck. Simply because we're using the same controller for this filtered half-H as we did in the simple buck in our previous video. Let's feed this system a reference voltage step from 0 to 0.5 volts and watch the response of the system. This will provide the step response of our controller. I want to take a moment to point out that this isn't the unit step response since we stepped from 0 to 0.5 volts instead of from 0 to 1, but we had to do this because a unit step input would cause the high side FET to latch on since the requested voltage would be higher than the possible output voltage for the system, so it would provide a very misleading result. With a known step response and a known load, we should be able to accurately replicate this system with our software control loop later on. This exercise will confirm two things: that the simulation is adequately representing the system, and that our software's sampling and control loops are operating as expected when we do the same step on our microcontrollers and hopefully see the same step response on the output. The simulations confirm that this hardware architecture should satisfy our requirements for the proof of concept test platform. Therefore, we're free to start designing it. With the hardware path defined, there is still another half to the story, and that's the controls and control loop. Typically, I'd have the whole story figured out before we start talking at all, but I want this to be a collaborative series. Therefore, I haven't finished this part of the project yet. We need to find a great tool to design our control loop in, because I like to stick to free tools when we're talking so folks who don't have $2,000 lying around for a Simulink license, like myself, can take a look at what we're doing for themselves and learn something. There's a lot of great learning opportunities throughout the design and simulation parts of this project, even if you never end up building a physical board yourself, which, if you recall, you should stay safe and never try to build this anywhere unless you have a proper education and certifications issued by a local authority. With that out of the way, I've used a free MATLAB-like tool called Scilab with great success. I'm not sure if they have the same filter building and control system modules we'll need, but we'll dive into the feature set of the Scilab feature suite in a future video, perhaps during a live stream? Once we design the control loops, it's just a matter of taking the coefficients and pulling them into the PID loop running on our microcontroller. We have defined some requirements for Project Darwin, and we're ready to move forward. We're well on our way through the proof of concept phase. Subscribe to be notified of our future videos where we'll design this test platform, dig into the control loop design, characterize our system's performance, and ultimately keep pushing this design forward. I think that kilowatt power supplies are great. If you think this proof of concept board will be awesome, let me know by hitting the like button on this video or leaving a comment down below letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone. Thank you for staying till the end. Bye!